Good day. My name is Clément Fortin. I'm a professor here at Skoltech in the Digital Engineering Center. And this is a design and system thinking class and laboratory. And we will show you what we do here. So we are in the laboratory. And I'm going to introduce to you the system thinking group, which I've created 2 years ago today. It was our first meeting. So it's a kind of a celebration at the same time. We had some people online. Now they're not with us, but let me introduce to you Jana Brovard, who's fourth-year PhD student, Andrei Pimenov, also fourth-year student, and Carolina is working on her PhD thesis now. So we will give you a brief overview of what we do here. So if you look at modeling languages, today there are many ways to model complex products in reality. So we can go back to the 1800s there, but in the last few years, there is a new thing called digital mock-up, which means we can put the whole product into one on the screen on a computer with all the solid, where the materials are and everything else. There's also very powerful analysis tools, which are model-based design there for CFD, which is computational fluid dynamics and finite element analysis. And then on the system side, there is, started with system engineering at NASA, but then there are model-based system engineering, and SysML and OPM are some languages to represent the architecture, and we'll show you very briefly what we can do here. And today, we're talking about digital twins, meaning can we have a digital reality that's very, very similar to the physical reality of an airplane, of a satellite, of a car, of many things that we have today. And this whole, all these three streams join to create now what we hope in the next coming years, what's called digital engineering. So, like I said earlier, system engineering, which is at the base of system thinking, is about dealing with complexity. What we know today in the world, and I'm sure you see it, is that complexity has increased so much that we need to find ways to treat it. So the Apollo program in the 1960s looked at this and started system engineering. Now, if you look at system thinking and digital engineering from another point of view, it has design, development, production, and service, and initially it was called computer-aided design, computer-aided engineering, and computer-aided manufacturing. But then at the system level, we moved to the virtual mock-up, the virtual prototype, and the virtual production. So it is at all levels. And now we have at the system physical, cyber physical system, where we talk about digital twins, virtual reality. And this is the level of digital engineering, and system thinking is all about this, looking at the overall view. And there's still a lot to be developed there. I will now give the floor to Carolina, who will talk to you about a particular case, which is called urban air mobility, system of systems.
So as Clément was mentioning before, our group basically focuses on understanding what we can do in order to reduce the complexity and the uncertainty of several systems. What we have here on the screen is a use case that we are currently working on. It's called urban air mobility. This is considered a system of systems. The scope of urban air mobility is to bring what we currently have in terms of aviation and develop it and improve it to develop air transportation systems that will move people and will move cargo between places that were previously not served or underserved by aviation. So what is it required to have urban air mobility systems? We need them to be affordable. They need to be quiet, so very low noise. They need to be fast, and one of the most important things, they need to be scalable. I'm looking personally into understanding what is the effect of technology insertion in system of systems. So what you have here in the picture is basically represented, it's a representation of what NASA believes should be the next step into urban air mobility. they had a call for proposals called NASA Grand Challenge. The complexity here arises because you're introducing new or improving current capabilities into an established operational system. So if we talk about urban air mobility, in that case, it would be the current aviation picture that we have. So when you bring in new technologies, you will have replacement, upgrading of technologies, infusion, diffusion. Here at Skoltech, we have several courses that help students focus on these kind of projects. And one of them is the systems engineering course. The last version of it was held last year, and their students actually focused on understanding what they can do in order to improve urban air mobility systems. So now I will give the word to Andrei, who will talk about us a bit more.
So, hello everyone, I'm Andrei Pimenov. I'm a fourth year PhD student here in Skoltech, and let me show the project, which is Air Taxi, which we made in the system engineering course in the December last year. So, so each engineering project starts from the mission, and our project starts from the mission too. So, the mission of our project was transport 6 passengers from Skolkovo to Vnukovo airport, and vice versa with Air Taxi. So, and then we moved to developing a success criteria for this mission. So, so system engineering starts from the estimation the success criteria of the requirements of the project. So we start working with our clients, we work with regulator, and we formulate 9 blocks of requirements for the real Air Taxi. But of course, we do not make a real Air Taxi on the project. We have to make some kind of prototype. And then from these requirements, we made requirements for our prototype. So on this part on the slide, you can see these requirements. I skip a lot, but here it just this idea that we start when we formulate the requirements, we move to the architecture. So this is system architecture of the real Air Taxi. So it consists from the Air Taxi itself and the system around it. For example, airport and server and passengers. Passengers is also part of the system, but it's part of the big system, not as Air Taxi itself. And then we move to the system architecture of the prototype of the system. So in our case, it was very simple. It was a drone from Geoscan company, and we program it just to avoid, and we program that drone that make this drone avoid obstacles during the flight. So this is a concept of operation from the one paper, a very important paper which we read, and this is based on the NASA. So this is how 4D corridors looks in the real application. So you see it. So around airport we have different zones, and just to going inside the airport, for example, in our case, this Air Taxi moving inside the airport of the Vnukovo. So we have to enter this 4D corridor. So on the left side of the slide, you will see a virtual environment simulation of this. On the second part of the slide, you can see the map. So on this yellow circle, this is Skoltech. Green circle, this is Vnukovo Airport. So this is the pathway of our Air Taxi. And you can see the different air zones. So air zone, and here we have enter to 4D corridor to the airport. So on this slide you can see as a visualization of this. So we have Air Taxi, and this Air Taxi just sending data about 4D corridor to the airport, and vice versa. So on this slide you can see the avoidance. So around each Air Taxi we have special zone, special safety zone. So and this is our test, our simulation. So we made it inside the Skoltech. So you can see the path, and here you can see the corridor. So in this case, our air taxi, and in our case this is drawn with Lego minifigures, goes in automatic mode inside this 4D corridor. That's all. Thank you for attention.
So, hello guys, my name is Jana Brovar. I'm also a PhD student at Digital Engineering Center and a member of System Thinking Group. So I will present you another use case that we are investigating with our research group. It is an engine aircraft pylon. It is a critical system for the research as it supports and provides the function of the engine, as it supports the thrust providing, electric power providing, and also connects the engine to the airframe and supports cooling and heating of passenger compartment. Thus, we should make an attention of that system as at a critical point in the aircraft design. One of the tools that could be used for the system components analysis is the design structure matrix that is presented here. Design structure matrix is a tool that supports network modeling, providing the analysis of system components and its relationships. DSM could help us not only to analyze the system architecture, but also could provide the analysis of system behavior, as we could analyze the interaction between each of the components. As an interaction, I mean the different flow, for example, the flow of material or some fluids, flow of electricity, and this interaction is exactly what bring the system its value. That's why this tool helps us to have a deep analysis of the pylon architecture. So here in the green zone, we can see the internal interfaces and the pylon, and the gray zone represents the external interfaces with airframe and engine. So for our research purposes, we use different tools in our research group, and this is only the one example, but there are much more of them, and we are also looking for the integration of all these tools to have the more productive product development process. So thank you for your attention.
So dear students, we gave you a brief introduction, overview of some of the work that we're doing, the research work, and you are most welcome to apply. You heard from PhD students, but we are very, very open to master students in research projects. We will teach you the basics, and from there, you can go on your career or decide to go for a PhD. So we're really looking forward to see you all. Bye-bye.